As time passes, artificial intelligence, or AI, is getting closer to our lives. As it is being applied to a great number of fields, more and more human beings are having to communicate with AI. In order to create a bridge between humans and AI, the human-AI interaction is born. Human-AI interactions try to give proper solutions to the communication of both actors, taking into consideration that AI solutions can be software applications or can be embodied, such as in cobots. With the goal of improving communication between humans and AIs, different types of applications are being developed. These applications could help with sharing or receiving direct feedback from the AI. Some of the more popular examples are virtual reality or VR and brain-computer interfaces. Virtual reality is a human-computer interface simulation of an environment that the user can interact with via sensory devices. This technology allows the user to experience a quite accurate sensation of what would really be felt in that environment. Some of the most common examples of VR can be seen in the gaming industry. On the other hand, brain-computer interfaces, or BCIs, are computer-based systems able to measure electrical brain activity and convert it into commands that will be interpreted by an external device to perform the desired action. BCI can be invasive, applied directly into the brain, or non-invasive, where the sensors are applied to the scalp, measuring the brain's electrical activity. A famous example of invasive BCI would be Neuralink, and for non-invasive BCI, a wheelchair controller. This morning, Fast-E has received good news. They've been hired for a new job. In this job, Fast-E's going out of their comfort zone, and they will receive VR training to get used to their new duties in the factory line, working collaboratively with cobots. In order to track how Fast-E evolves during their training, they will wear an EEG headset that will record their emotions in real time, making the simulation adapt in correspondence. At first, Fast-E is very nervous, but as they receive instructions from the VR, they get a bit more comfortable. After several training seasons, they improve their skills and emotional levels through a VR simulation, which means that they are ready to be implemented into real-life scenarios. For several days, Fast-E has been exposed to various tests and VR trainings to determine their emotional profile. After all the training, Fast-E's emotional profile and abilities have been calibrated. So, it's time for Fast-E to go to the shop floor. Fast-E will perform the same collaborative task that was trained for in the VR, but now with real cobots. While facing their job, Fast-E is stressed at the start, but thanks to the EEG headset and to having a previous profile, the cobots can adapt to Fast-E's cognitive state, making the tasks look very easy and risk-free. Watching the adaptations of the cobot, Fast-E feels safe and confident about their abilities and their new colleagues, the cobots. After some time working collaboratively with the cobot, Fast-E's abilities to perform the assembly tasks have improved greatly, and they are very happy with their work colleague. This paper presents an approach for adapting cobot parameters to the emotional state of a human worker. The approach utilizes electroencephalography for digitizing and understanding the human emotional state. Afterwards, the parameters of the cobot are instantly adjusted to keep the human emotional state in a desirable range, increasing the confidence and trust between the human and the cobot.